So I'll start at 6-5. There are any more people? Okay, so what I'm going to do is I'll write the problem and I'll give few minutes to solve on your own so that you will also have practice during this session only. And at the end of the 5 minutes or so, I'll definitely solve this problem. Okay. Okay, so the question number one is so please try to attend this question. So the question is as per Bohr model, the minimum energy required to remove an electron from the ground state of doubly ionized lithium atom, whose atomic number is Z equal to 3. What will be the energy, basically, minimum energy? So please try to attend this question and then we'll discuss. By the way, is my voice clear? Can someone please confirm?
Yes,
Hello.
sir. Clear, sir.
Okay, okay. Thank you.
Clear, clear.
Still joining. So anyone have the answer or should I solve the problem? Hello. Please be interactive. Otherwise, it will just be I'll come solve some problems and go. Otherwise, it will be difficult to track the progress and okay. So let me solve the problem. So we have lithium atom. So suppose this is a nucleus and there are two orbits around that. Sorry for my pathetic drawing, but essentially, so yeah. So two electrons will occupy this, and then one electron, Z equal to 3. Now, what the question says is that the lithium atom is doubly ionized. What this necessarily means is two electrons are pulled out of this atom. So then it essentially becomes like an hydrogen atom, one nucleus, and then with one electron, basically, right? But the point is here the Z is 3. So what do we know? For let's say, so the energy, electron's energy at the nth orbit, the general formula is given by minus 13.6 Z square. Z is the atomic number by n square in the electron volt unit. If you put Z equal to 1, then it is obviously this is for a hydrogen atom with Z equal to 1, proton number is 1, and here we have given Z equal to 3 lithium atom, and since this is in the first orbit itself n equal to 1, So minus 13.6 into 3 square by 1 square. Minus 13.6 into 9 ev, which will be around 122.4 ev. This is negative energy because this is a binding energy, right? So the electrons are bound to the nucleus. Now if you want to pull out that electron from the ground state or remove the electron from the ground state, you need to put an extra amount of energy. This amount of energy you need to put. So the actual amount of energy needed to remove the electron is 122.4 ev. The correct option is B. Okay. So anyone have any doubt, please feel free to ask questions. Okay, so the second question we are going to solve is the question is following. So the question is the following: niobium crystallizes in BCC structure, means body centered cubic structure, and it has a density of 8.55 gram per centimeter cube, and the atomic mass is given as 93. So what will be its atomic radius? Options are 143.1 picometer, 158 picometer, 14.3 picometer, or 205.2 picometer. So again, what I'm going to do is give some time to solve. Whoever solves it, please tell me the answer, or put it in the chat box. Okay, so let me solve the problem. So we have a niobium crystal which is body centered cubic structure. So what is meant by body centered cubic structure? So let me draw some cartoon picture. Please try to draw. So in the body centered cubic structure, so there is atoms at the corners. All the corners are filled by some atoms, and in the middle there is another atom. That's why it is called body centered structure. Now in an unit cell which has body centered structure, it will have how many number of atoms? It will have two number of atoms. Why? Because these corner atoms are part of 8 unit cell, above, side, left, right, above, below. If you count it, then it will be part of 8 unit cell. So how many atoms are there? Like this one, 1 2 3 4, so 8 are there. So it comes like this one, 8 into 1 by 8, it's a part of 8 unit cell, plus in an unit cell this body centered atom is itself only within the unit cell, so 1, so it comes as 2. Now there is a formula which is the density of atoms in the unit cell are given like this one. So I'll explain how this comes, although not derived fully, but we'll tell the physics behind this or the mathematics. So here the density of atoms in the unit cell is given by rho, where n is the number of atoms in the unit cell given by 2 in our case. M is the atomic mass, which is in our case it is 93, and A is the side of an unit cell. This is A. Okay, so since it is cubic, so the volume will be V equal to A cube, and the other this part n m by na, na is the Avogadro number, n m by na represents the mass of atoms in an unit cell. So in, because this is atomic mass and this is Avogadro number, right? So it essentially gives us the total mass in an unit cell divided by the volume of the unit cell. Then we get mass by volume, the density. So in our case, rho is given as 8.55 gram per semi cube, and we have n. Okay, so let me write n equal to 2 and m equal to 93, and what you need to find atomic radius a, so a cube, and then Avogadro number, which is 6 point happened 6.22 into 10 to the power 23 per okay, mole. So if we put all of these and calculate A, or rather A cube, no, so let's directly calculate A. It will be around cube root of 2 into 93 by 8.55 into, so this will come around 3.306 and into 10 to the power minus 8 centimeter. Okay, so now see read the question again. It says what is the atomic radius, not the unit cell dimension. A is the unit cell dimension. What I need is this atomic radius, right? So the relation between atomic radius and this unit cell dimension is given as, if r be the atomic radius, then it is root 3a by 4. So how can we get it? So although the picture is kind of giving wrong impression, but what really happens is that these atoms, this corner atoms and then center body centered atoms and then another corner atoms, so this basically touches each other. So from there you can find it. Okay, so if we calculate this, root 3 into 3.33306 10 to the power minus 8 by 4 centimeter, it will be around 143.1 picometer. Calculate this. 143.1 means option A is correct. Okay. So let's move to the next one. Next one is the question which says okay. Let's solve this.
Sir, good evening, sir.
Yes.
I think I already discussed that question, sir. First
In
class.
okay. Okay. Sorry, I didn't know. Okay.
Okay, no
So
problem.
okay. So should I discuss this or better will be to skip this one?
Okay, no problem.
No, I mean, what about others say? Should I solve the or the skip? Can anyone else few more comments? Okay, so I'll solve it quickly. Give no time to you. Okay. Okay, so I'll directly solve this one. So the potential energy function for a solid is expressed as u of r. This term is the okay. So potential energy. So this term gives the attractive, and this is the repulsive. And then we need to find the potential energy at the equilibrium. So for equilibrium, the potential energy with respect to r is the interatomic distance. So at the equilibrium, the potential energy will be minimum. Okay, so for this situation, we have del u del r equal to 0. So if you take derivative of this term, then it will be 6a by r to the power 7 0. So let's say r equal to r naught is the equilibrium position. So then it will be 6a by to the power 6 will be 2b by a. Okay, and we need to find the potential energy at this equilibrium r naught. R naught will be the 6, yeah, but essentially it will be better to keep it like that. We'll see. So potential energy at r equal to r naught is given by minus a by r naught to the power 6 plus b by. So the final answer will be minus a square. So you notice that at equilibrium the potential energy is negative, as it should be, because negative potential energy essentially means there is attractive force, right? There is attractive force between uh, two atoms separated by r naught. That's why it is the equilibrium. If they are in the repulsive force, they will not be in equilibrium. So okay, so let's move on to the next problem. Okay. Okay, so a crystal belongs to the face-centered cubic crystal, and the dimension of the unit cell is 1 nanometer, whereas the size of the crystal, the full crystal, is 1 centimeter. Now the question is the number of atoms in the crystal. We have four options: 2 into 10 to the power 21, 4 into 10 to the power 21, and 2 into 10 to the power 23, and 4 into 10 to the power 20. So let's try to solve it. I'll give some time then. So please, if you're solving the questions, then please put it in the chat box or just unmute yourself and tell me. Anyone solving this question? It should not take much time actually. Okay, so let me solve it. So what we have, the dimension of unit cell. So this dimension is 1 nanometer, 10 to the power minus 9 meter, or 10 to the power minus 7 centimeter. Now the crystal is made up of, many Avogadro, of the order of Avogadro number of unit cells, and the crystal size, the total crystal size is 1 centimeter. This is 1 centimeter. So nothing they have mentioned in the question means it is also cubic. Okay. So the crystal itself is cubic, and the unit cell is also face-centered cubic. So the what we need to find the number of atom in the full crystal itself, not in the unit cell. Okay. So in one unit cell, the number of atoms for a face-centered cubic crystal is 4. So how does it come as 4? So try to do very quickly. So again, from all the corner atoms, you will have 1 by 8th contribution to a particular unit cell, and there are 8 such Okay, so option B for this one, right? For question number. Okay. Uh, yes, Kalpana, you are right, but still I'll solve it. Okay. So from 8 corner atoms, there the contribution is 1 by 8 into 8, similar to the previous case. And then at the face, there are 6 more atoms will be there. And in each face of the cube, it will be very difficult to visualize. But how many faces does it have? 1, 2, 3, 4, 5, 6. So 6 faces will be there. And that means there are 6 atoms associated with this unit cell itself. But each face center or the atoms in the face contributes to its unit cell at the very next to it, right? The nearest unit cell. So the contribution for this unit cell will be half. So then 1 plus 3 equal to 4. So this is how the coordination number or the number of atoms in a face-centered cubic crystal becomes 4. So what we need to find is how many unit cell are there in the crystal itself. So volume of unit cell will be, let me put it in the semi cube itself, one cubical, and volume of crystal will be, okay, sorry, this will be nanometer cube. So this will be 10 to the power minus 7 cube semi cube, and the volume of crystal will be 1 semi cube. So how many unit cell are there? So number of unit cell will be 1 semi cube by volume of unit cell, 10 to the power minus 7 cube. So it will be 10 to the power 21. So 10 to the power 21 number of unit cell is there. Now in each unit cell there are 4 atoms. There are 4 atoms. So the number of atoms in the full crystal will be 4 into 10 to the power 21. Okay. The next question. Okay. So the question is silicon has a diamond structure with cell edge A equal to 0.542 nanometer. Now we need to find the interatomic separation. Let's try to find out. Wait for 2 minutes and then we'll start solving. By the way, one hint I'm giving, the diamond structure is face-centered cubic. Okay, that will help to solve. No, Dhanush, option D is not correct because the cell edge dimension itself is the 0.542 nanometer. So the interatomic separation is different from the cell edge or the dimension of the cell. Okay, solve the problem. Others, anyone tried? What you got as an answer? Okay, so let me try. So let's try to understand what is interatomic separation and the unit cell dimension. Okay, there is subtle difference. So diamond structure is basically face-centered cubic. So FCC structure. For FCC, the atoms are like this one at the center. Sorry, this is not circle, but okay. So So this is a unit cell dimension, and this radius is, let's say, r. This is at the face, okay, this face, this face. So, so if the atomic center is here and all these atoms touches each other, then what is the distance? So this will be r, this will be another 2r, and this will be another r, right? So this total corner will be 4r, and what is the value of this corner or the edge in terms of a? This is a, this is a, and this is a right angled triangle it is forming, right? 90 degree. So this will be a square plus a square, right? So root 2a, 4r equal to root 2a, and r, basically r is the radius, so the interatomic separation will be 2r, right? So by interatomic separation we mean the center to center distance. This one will be 2r. We need to find what is the 2r for this case. So the interatomic distance or the diameter equal to d equal to 2r, and which will be a by root 2, 0.542 by root 2 nanometer. So if you calculate this, this will be around 0.383 nanometer. Okay, so the correct option will be C, not D. And yeah, did you guys understand that interatomic separation means this one, not the unit cell dimension or the cell edge as is written here? Okay, it has to be less than the unit cell dimension. Okay, so the next question we are going to solve. So, can you anyone confirm that packing fraction and all these concepts are covered up to week 2? Hello? Did you guys know about packing fraction? Anyone please write in chat box or tell me.
What, sir?
Packing fraction. It is not covered, right? Then
Covered. Not covered, sir. I
okay.
think atomic radius and Miller indices like that.
Okay. Thank you. I'll skip this. Okay, so Miller indices has been done. Okay. Okay, so I'll come to Miller indices later. Let me do another problem related to unit cell dimension and volume itself. So the question is sodium transformed from body centered cubic structure to hexagonally closed packed structure, HCV structure basically at 23 Kelvin. But the important point is without change in density. Okay. So where this is given that the cubic phase in the cubic phase, the unit cell dimension is 4.23 angstrom, and the hexagonal closed pack phase, the C by A ratio is 1.63. So what is C? C is this vertical uh, dimension and A is this lateral dimension or the in-plane dimension. Okay, so hexagonal or hexagonal closed plate structure. Now, what is the lattice constant in the HCP phase? That we need to find out. So please try this one. This is, I think, a nice problem. Finally, I'll try solve. Yes, Lakshmi Priya. The answer is A. I'll solve it. Okay. So, so the density remains same, and the sodium itself converts or transforms from BCC to HCP. Okay. So the mass remains same here. Okay, because the same amount of mass is transforming to another phase. So mass is basically volume into density. Now it says density also remains same along with mass when it transforms to another phase. So essentially volume in BCC structure is same as volume in HCP structure for this problem. Now what is the volume for the BCC structure? BCC structure is simply cubic, right? So it is A1 cubic. Let's say in the BCC phase the unit cell dimension is A1. And what is the volume of a HCP crystal? So it's complicated to calculate. It's not complicated mathematics or physics wise, but it's a lengthy and visualization has to be there to calculate this volume of HCP phase. So I'm skipping that, but essentially it is given by this formula A2 square C, where A2 is this hexagonal, so something like this one. So A2 is this one in plane, and C is out of plane. Okay, C is dimension of the vertical dimension. So we have this C by A, or rather A2 here, ratio as 1.63. So we'll use that one to find A2. And A1 is given by 4.23 Armstrong. So A2 will be cube root of 4.23 Armstrong cube, and then 0.3 into 1.63. This is also given Armstrong. So by solving this, we'll get 2.61 Armstrong. That is option A is correct. So let's move on to the next problem. So again, so please feel free to ask questions. If you don't understand anything or any doubt, please feel free to ask questions. So in a tetragonal lattice, two dimensions are same basically. A equal to B equal to 2.5 angstrom and C is 1.8 angstrom. What is the lattice spacing between 111 planes? So this is basically two adjacent 111 planes. This is an easy question. Try to solve it. Anyone solve it? Okay, so let me solve this. So given are the planes whose Miller indices are like this 111. Okay, so the distance between two Miller indices having each KL and the dimension as A, B, C is given by this. Okay, so in our case, HKL is 1 and A and B is 2.5 each. And C is 1.8. This will be Angstrom. So if you calculate this, you'll find this will be 1.26 Angstrom. That means option C is correct. Okay, so let's read that Miller indices, right? So next problem. Next problem will be
Sir, good evening, sir.
yes.
Sir, sorry for the interruption.
No.
Sir,
Okay.
in our second assignment based Miller indices problem workout means useful for solve the problem, sir. I think Miller indices planes only given the arrow mark based or value based, sir.
Okay.
That based problems you discuss means that is useful for solve the problem, sir.
Sorry, I don't get you properly. Your voice is breaking. Hello. Can you write in the chat box? Hello. So anyone else who understood what she or he was trying to say? Yeah, tell Kalpana. Okay, okay. Diagram based problem useful for assignment. Uh, okay, let me see if I can give you any diagram based problem. Okay, I'll see. Let's see. I'll solve some problem based on diagram. Okay, so let's see. If I'm moving to diagram. Okay. So find the Miller indices for planes which intersect ABC. What is ABC? ABC is basically three Cartesian coordinate dimensions. Okay, A, B, and C. At for problem number one, 3A, 3B, 2C, and then A, 2B, and infinity. So yeah, Miller indices lectures are there in week two, most likely. So please try to solve these two problems. I think this will clear the concept more about the Miller indices. So please try to attempt this and I'll solve this. Okay, Renuka Devi, you are right. Both the Miller indices are right. So anyone else solve the problem? Please feel free to ask question and please be interactive. Okay. So the first problem, the plane intersects these coordinates at let's say 3A, 3B, and 2C. So the plane is somewhat like this one. Okay. Now the way to find Miller indices is the dimension along that direction by the basically the intercepts, right? So 3A and then B direction. In this direction, the intercept is again 3B and then C by 2C. This direction. So what is that? 1 by 3 is to 1 by 3 is to 1 by 2. Now, one can write like this one, but it is not advisable. Standard practice is to do it in a full year. Okay, just do the LCM of all these things. So then it will be 2 is to 2 is to 3. Okay. So for first problem, this is the Miller indices 2 to 3. People also like write like this one or this one also. And for the second problem, the intercepts are A, 2B, and infinity. So what is meant by infinity basically, right? So along this direction, the plane never intercepts. That's why it is infinity. Or in simple words, the plane in the question is parallel to the c direction, right? This will have intercept at, let's say, a and 2b. Some plane like this one maybe, where it is parallel to the c. Okay. Then again, following the same procedure, a by a in this case, b by 2b, and then c by infinity equal to 1 to half is to 0. So 2 is to 1 is to 0, or 2 1 0. I think these two problems regarding the Miller indices, you guys will be able to solve all those diagram problems. Okay. Next. Okay, so okay, so the question is the ratio of magnetic dipole moment to the angular momentum of electron in the first orbit of hydrogen atom is given by E by 2m, or E by m, or 2m by E, or m by E, where E is the electronic charge and m is the electronic mass. try this. This is very easy question. So okay, many people are getting right answer. Okay, so let me see. So the formula for magnetic dipole moment, current in the loop. Let's say I have a circular current loop and the area of that. And in this case, the current will be in the hydrogen atom. There is single electron around the nucleus. So electronic charge by the time period for the first orbit itself. Now the time period is given by, for the nth orbit, the general formula is n h bar by 4 pi square m r square. Right? This is radius of nth orbit basically. So sorry, this is T inverse. This is the frequency. Okay? So it will be, and the area for this first orbit, let's say pi r n square. So magnetic dipole moment in mod value of that, pi r n square into n h bar 4 pi square n square. We have to find the ratio of magnetic moments and the angular momentum. So the angular momentum L is given by n h bar, right, for the nth orbit. So the ratio is m by L equal to, so few terms cancel and it comes out as a E by 2m, m by L. So E by 2m, A is the right answer. Okay, so next question is, So the question is circular disc of radius 1 meter each are placed on a plane so that it forms a closely packed triangular lattice. Now we need to find the number of discs per unit area. Okay. So yeah, try to solve the problem. Meanwhile, I'm trying to draw the picture of this problem. Okay, so the circles are supposed to be of same size, and these are the triangular structure basically. So we need to find number of these discs, small discs per unit area. Try this one. Anybody solve or trying to solve?
Sir, once explain, sir. No idea.
Okay, okay. So, okay. So this same structure supposed to be same at least. So this same structured the circular discs. Okay, they are closely placed to each other, such that they forms this triangular lattice. How do they form triangular? This is a triangular. This is another triangle. This is another triangle like this. Okay. So what we need to find, given that the radius, given that the radius of each circle is 1 meter. Now what we need to find is number of discs per unit area. Okay. So how many number of discs will be there per unit area? So this will be. So am I clear or need to more elaborate? Okay, let me solve this. So so these circular triangles, sorry, circles or the disc forms a equilateral triangle, because if their size is same, then they will form an equilateral triangle, right? And what will be the side of that equilateral triangle? This side will be a equal to 2r, right? The radius r is the radius of this. So side is equal to 2r equal to 2 meter for these equilateral triangles. Now the what is the area of these equilateral triangles? Root 3 by 4 into side square, right? So the area will be root 3 meter square, area of each triangle. Okay. Now, how many discs are there in a triangle? That's not the question you need to ask. So the number of discs, or let's say inside a this is, so If we focus on this triangle, then how many discs are there connected to this triangle only? So one, two, right? Okay, fine. So if we focus on this triangle itself, then there are three circles or discs around this one, right? So now 3 into what we need to find is three circles are there or discs are there, but each disc contributes to six such triangular structures, right? This is becoming nasty, but if you look at it very carefully or think about it, then this will be easiest too. Okay, so if you focus on this triangle, the middle triangle, then around this there will be six such circles. So that's why we have 1 by 6, which will come out to be, sorry, half. Now this is the number of discs inside a triangular lattice, right? And we need to find the number of discs per unit area. So we need to divide it by this area. So this will be 0.29 meter to the power minus 2. So C will be right option. Okay, so maybe the last problem of today's session. Okay. I'm not writing these parts. Basically, the crystals are mixture of so the question is metallic copper is known to form cubic crystal. We have not told that it forms simple cubic, body centered cubic or face centered cubic. And given the lattice constant measured from X-ray diffraction is around 0.63 nanometer, and the density is given, molecular gravity is also given. So we need to find what type of crystal it is, simple BCC, FCC, or the mixture of both BCC and FCC. Now one can actually remember this problem because copper is a very common metal and we study copper everywhere. But the idea of the problem is not to remember and say the answer, rather to find mathematically supporting the logic. So anyone have any idea how do I solve this problem? Anyone or anyone doing the problem? Okay, okay, I'll solve it. Just 2 seconds. So let me solve. So the idea is very simple actually, and you all know that. So for BCC, FCC, or simple cubic, or even hexagonally closed packed, all of these different type of crystal structure have different coordination number, right? Or the number of atoms in all these crystal structures, unit cells are different. So if we can find the number of atoms per unit cell somehow, then our problem is solved. Then we can actually identify it is FCC or BCC. Just we have to remember that coordination number of each type of cubic crystals. Is the idea clear? So it will be clear when we solve the problem. So again, so we know the density formula is given by n, the coordination number or the number of atoms per unit cell, m is the molecular weight, and then there is a cube, all are cubic crystal. It is already mentioned that cubic crystals, and then there is Avogadro number. So every other thing is given, density is given, m is given, and a is also given. So what we need to find is n or the coordination number. So n will be rho cube in a by n. So, so the density rate 0.96 a cube and then there is Avogadro number. Molecular weight is given. If we solve this, calculate this will actually come out to be 3.97, which is around 4. Now, which crystal structure or the cubic crystal structure has 4 number of atoms per unit cell? It is FCC, right?
Easy.
So it is FCC. For BCC, it is probably 2, right? So this is how we can find it. Okay, so it's already 8. So let me stop discussing this problem. But before ending this session, I would actually like to take your feedback. I mean, so feedback in terms of everything, the kind of problem that I'm solving, is it relevant? How do you feel? Or is it frequently clashing with others who have solved those problems? Because anyway, we don't know what others have done. Okay, so there is no way to know other than mailing each other again and again. So please feel free to give feedback. It should be open actually, because next time so that I can improve upon.
Thank you, sir.
Just write in the chat box or just unmute and so do you think are these problems becoming relevant or what? Feel free to okay, okay. So we are also students, so don't follow so much protocol. In a sense, we have to follow that, but when it comes to the feedback, we need genuine feedback to improve upon. Okay, so let's end today's session here. Thank you everyone for joining, and let's hope that you will continue to join in all those sessions over the weeks. So I'm ending the meeting. Okay,
Thank you.
Thank you, sir.
thank you everyone.